Hello everyone. For today we're going to be taking a look at section 9-2, which is all about tangents. Now we've learned earlier that a line that's tangent to a circle intersects that circle at exactly one point. So you need to keep that in mind because we're going to be talking about this and this idea of tangent lines a lot in this video. So just keep in mind that a tangent line, it intersects a circle at one point. Sometimes I think of it as, is it just as the line is going by the circle, it just barely touches the circle and then keeps on going, right? So we have several theorems that we're going to be taking a look at, and then we're going to apply those theorems to a couple example problems. So let's just jump right in and start going through these theorems and some definitions as well. All right. To start off with, we have theorem 9-1, and it says that if a line is tangent to a circle, like we have line N right here, tangent to circle A, then the line is perpendicular to the radius that would be drawn to that point of tangency. I already have point over there, so I just need the point of tangency. We don't need that there. So what that means for this picture here is that we could say that if N is tangent to circle A, then that would indicate that segment AB, which is a radius of circle A that's drawn to the point of tangency at B, it's perpendicular to line N. It would form a 90-degree angle right there. So that's pretty straightforward, not too complicated there. One of the things that we can learn from that, if we kind of extended this idea of perpendicular, of this being perpendicular right here, it would extend to an idea that tells us that all tangents from a point to the same circle are going to be congruent. And there's a kind of a nice little proof of this that we're not going to get into right at this point. But what it would tell us is that in a picture like this, if segment GH and segment GI are both tangent to circle E, then we can conclude that segment GH would be congruent to segment GI. That's what the corollary to theorem 9-1 would tell us. Again, nothing too complicated there. If we have this point G that's outside the circle and we draw the tangents to circle E from point G, so G to H and then G to I, those would be congruent to each other. Our next theorem says that if a line in the same plane as a circle is perpendicular to a radius at its outer endpoint, so in other words, we have line M right here that is perpendicular to segment ST, which is a radius of the circle, then the line is tangent to the circle. So this is, in fact, this is basically just the converse of theorem 9-1. It's telling us that if M is perpendicular to segment ST, then M is tangent to circle S. A few more things you need to know that relate to the tangents of circles, a few more new terms. First of all, if we have a line that's tangent to each of two coplanar circles, that would be called a common tangent. And then we can break the idea of common tangents down. We can break that down into two further kind of differentiations. We have here a couple diagrams. You can see there's two diagrams here that both show a line that's tangent to two circles, a big circle and a little circle. So we have this line here that's tangent to the big circle and the little circle here. And then we have this line here that's tangent to the big circle and the little circle on this lower diagram. And you can see that they are kind of slightly different. You notice there's this dotted line right here. And that segment is connecting the centers of the two circles. In each diagram, you have a dotted line connecting the centers of the two circles. And the difference, of course, is that in the top diagram, that common tangent is crossing over or intersecting that segment that's joining the centers. In the bottom diagram, it's not. It's not crossing over or intersecting this dotted line that connects the two centers of the circles. And that's the difference that we're talking about here. In this top diagram here, what we're looking at, this thing right here, that is called a common internal tangent. So this blank here is for internal. It's intersecting a segment that joins the centers of the circle. So it's a common tangent, meaning it's tangent to two circles, and it's intersecting the segment that joins the centers, that dotted line there. This bottom diagram, this picture, this tangent right there, that is called a common external tangent. And just like internal and external are kind of opposites of one another, you can kind of guess that the definitions of common internal tangents and common external tangents are, in a way, opposites of one another. Because a common external tangent does not intersect the segment that joins the centers of the two circles that the line is tangent to. Right? So common internal tangents and common external tangents, just a couple more phrases that you're going to need to know. And lastly, another couple phrases that you're going to need to know is this idea of tangent circles. Tangent circles are coplanar circles that are tangent to the same line at the same point. So in other words, if I look up here at this example, I have two circles that are tangent to the same line. But these circles are not, they don't fit the definition of tangent circles because they're not both tangent to this line at the same place. This bigger circle looks like it's tangent at about this point. This little circle looks like it's tangent at about a point right here, not tangent at the same place. Down here we have a couple examples of tangent circles. We have these two circles, one of them is inside the other, that are both tangent to point K, or to line K at point V right here. And because this littler circle is kind of inside this bigger circle, this is an example of what we would call internally tangent circles. Those are called internally tangent circles. Over here we have another example where we have two circles, both tangent to line J at point G there. But you can see it's not like what we have over here with one circle inside the other. They're kind of on opposite sides of the line. Those are called externally tangent circles. So we have internally tangent circles, externally tangent circles, common internal tangents, and common external tangents. Just a few phrases that you're going to need to spend some time kind of understanding and being able to identify in a diagram. So let's look at, speaking of diagrams, let's look at a few examples of how we could put some of this information to use. In this diagram below, we have a lot of information that we need to go through about this diagram. It says that circle M, which is the littler circle, and circle N are both tangent at P. So they would be what we would call internally tangent circles. They're tangent to segment PR at point P. PR and SR are both tangent to circle N, which is the bigger circle. Circle N has a diameter of 16, so let me try and sketch in a diameter of N. Now my lines don't always turn out the straightest on this, so I'll do my best here. There's half of a diameter, or a radius, and here's the other half. So that line there has a length of 16. So that is 16 units long. PQ, so right here we have segment PQ. Q is some other point on PR. It's not a point of tangency, it's just a point on segment PR. That has a length of 3. RQ has a length of 12. And our job is to find these 6 lengths, all right? Starting with the length of PM. Now PM is a radius of circle M. It goes from the center of the circle out to a point on circle M. So it's a radius of this circle. If I think about the diameter of circle M, I would realize that the diameter of circle M is going to be half of the diameter of circle N, because circle M contains the center of circle N. So its diameter is basically a radius of circle N. So I know the diameter of P of circle M, or the length from P to N, that's going to be 8. So if I quickly kind of maybe sketch that in, I know that this would be 8. And then PM is half of that, right? Because PM is a radius of circle M. So that would mean that it's going to be 4. So PM has a length of 4. MQ is the next thing I'm supposed to find. So MQ isn't, there's actually not a segment on my diagram for MQ. So let's quickly sketch that in. Connect M to Q right here. So I have segment MQ, and I'm supposed to find that length. Well, I can use what I learned earlier on this video, and I can realize that this angle right here is a right angle. There's a right angle right here because the tangent PR would be perpendicular to segment PM or segment PN, either way you wanted to think of it. So that creates this right triangle here. I know two sides of my right triangle. I know the two legs of my right triangle. MQ, this distance I'm trying to find, is the hypotenuse of that right triangle. So I should be able to set up the Pythagorean theorem to find MQ. Since I know my legs, PM and PQ, those go where the A and the B are. So I'm looking at 4 squared plus 3 squared equals C squared, which in this case is MQ. Now some of you are recognizing right now that I'm looking at a special Pythagorean triple here. I have legs of 3 and 4, which you might remember what that means the hypotenuse is going to be. If not, let's go ahead and work it out. 4 squared is 16, 3 squared is 9, so 16 plus 9 is MQ squared. That means 25 is MQ squared, and the square root of 25 would be my length of MQ. And the square root of 25 is 5. So you guys might have noticed that this is a 3, 4, 5 right triangle here. This hypotenuse has a length of 5. Next, we're supposed to find the length of PR. And so we can just use the segment addition postulate and realize that the length of PR would be PQ plus QR, or 3 plus 12. So that's going to be 15. Not too hard there. The length of SR is, well, SR is a tangent, right? And so is PR. And we learned earlier in the video that all the tangents from point R to this circle N would have to be congruent. So if PR is 15, SR would have to be 15 as well. NS is the next thing we're supposed to find. Now I notice that NS goes from the center of my circle out to a point on my circle. So it's a radius of circle N, right? We already know that the diameter of circle N is 16, so that radius would have to be 8. So there's an 8 right there. And lastly, we have to find the distance from N to R. So let's go ahead and draw that segment in there. See if I can do it in a reasonably straight manner. So I have to find segment NR's length here. Now again, I need to remember that this tangent segment would be perpendicular to this radius of circle N. So there's a right angle right there, right? And I already know that this length is 15 and this length is 8, so I know two sides of my right triangle. I can use the Pythagorean theorem. I can use a squared plus b squared equals c squared to find NR. My legs are what goes where a and b are, so that's 8 and 15. And some of you might be recognizing this as another Pythagorean triple. If not, we can work it out. 8 squared is 64. 15 squared is 225. Oops, 225. So 64 plus 225 is c squared. That's 289 for c squared. So the square root of 289 is what the length of c is, or the length of NR is. And square root of 289 is 17. So this is an 8, 15, 17 Pythagorean triple. My length of NR is 17. So that's example one. There was a kind of interesting that there was so much information that we could take from this diagram based on just knowing this bit of information up here. The next example we have, a little less complicated, I would think. A little less complicated picture, not as much information than setup. All we know is that OT is tangent to circle R right here. But of course that means we know that there's a right angle right here. All right, we got to remember that. Part A says OR is going to be 6 and OT is going to be 8. So what would RT be? Well, we know that RT is now the hypotenuse, right? It's the hypotenuse of this right triangle. So I can set up another Pythagorean theorem problem. I can say that 6 squared plus 8 squared equals RT squared. RT is the hypotenuse, so it goes where the C is. And that gives me 36 plus 64 equals RT squared. 36 plus 64 is 100, so 100 is what RT squared is. So the square root of 100 would be RT, and this is a 10. So RT has a length of 10. Now in the next question, we're going to kind of ignore what we just figured out. We're going to ignore the measurements that we just had, so let me go ahead and erase those. And it says that if OT is 4 and the measure of angle OTR is 45 degrees. So if this is a 45-degree angle right here and this is a 90-degree angle, it means that this is also a 45-degree angle. And so what we're looking at is a 45, 45, 90, where this leg right here is 4. And we remember that from chapter 8, the hypotenuse of a 45, 45, 90 is equal to the leg times the square root of 2. And since RT is the hypotenuse, we would know in this example that RT is equal to 4 times the square root of 2, or just 4 root 2. So RT has a length of 4 root 2. Okay, folks, so that's it for this video. We learned a lot about tangents of circles and some interesting things that happen when you have the tangent drawn to a circle or to maybe a pair of circles. And so in the next video, we'll take a look at some more kind of terms and definitions regarding circles. But that's all for now, so we'll see you next time.